Consider the following problem. We have an elevator with two blocks in it, a 30 kilogram block that's resting on the floor of the elevator and a 20 kilogram block that's resting on the 30 kilogram block. This whole thing, elevator, blocks, etc., is accelerating downward at the rate of 2 meters per second per second. So your task in this problem is to determine and carefully specify the magnitude and direction of all the contact forces in the problem. For example, the force that the 20 kilogram exerts on the 30 kilogram block and vice versa and so forth. Now, this is a problem involving multiple objects. Now, in problems involving only one object, you can often get by with just using Newton's second law. But in this problem, we're going to need to use not only Newton's second law, but also Newton's third law in order to get anywhere. And so this is a very important example. Before we begin, I want to very briefly review Newton's third law. Newton's third law says that if you have two objects, let's call them A and B, that the force vector that object A exerts on object B is equal in magnitude and opposite in direction to the force vector that object B exerts on object A. Now some books will leave out the on between the two things, but I like to put it in there just to be sure we know what is exerting a force on what. If you write it this way, you'll never be confused. Now, there's some really important things to say about this. First of all, this is a relationship between two vectors. This vector is the negative of this vector. And that means equal in magnitude and opposite in direction. So I can immediately write the following, which to some people seems counterintuitive. Sometimes I'll write an expression like this and people will say, wait, where's the minus sign? Aren't they supposed to be equal and opposite? Well, first, let's put equal and opposite out of our heads. If things are equal, they can't actually be opposite. The full expression is this vector and this vector are equal in magnitude, but opposite in direction. This is just the first half of that statement saying that this vector and this vector are equal in magnitude. That's all it's saying. The opposite in direction is not in there because this being a relationship between magnitudes won't have directional information. So this is true, that's the full statement of Newton's third law, and this is sort of part of what's contained in Newton's third law, a relationship between the magnitudes of two forces in a Newton's third law pair. Alright, so we're going to need to use this and keep it straight. If you start throwing minus signs in relationships between magnitudes, you're not only going to confuse yourself, you're also probably going to actually make a real mistake. So let's get on with this example and see how it all plays out. In order to determine and specify the contact forces in this problem, we're going to need to draw a series of free body diagrams. And by the way, this thing here is not a free body diagram, that's a schematic. Now, there's lots of ways we can start this problem and do this problem. I'm not going to necessarily do it in the fastest way. I'm going to try to do it in a way that is illustrative. Okay, so I'm just going to start by looking at the 20 kilogram block, drawing a free body diagram of that. So here's our free body diagram of the 20 kilogram block. So I've drawn the box. I've labeled it with 20 kilograms just so I can tell it from the other free body diagrams. This is not a force, it's just a label for knowing what object I've drawn the free body diagram of. This 196 newtons, that's 20 kilograms times 9.8 meters per second per second. That's the Earth's gravitational force on this box. And this here is representing the force that the 30 kilogram block is exerting upward on the 20 kilogram block. And I've labeled it this way, with the arrow indicating the direction and then this magnitude representing the amount, F30 on 20. Now, the whole purpose of this free body diagram is just to write out Newton's second law and apply it. So let's do that. The sum of the forces acting in the y direction on the 20 kilogram block must equal the mass times acceleration in the y direction of the 20 kilogram block. So let's plug in the forces using our coordinate system with the positive y direction being upward. So So I have this upward and this amount downward, so I need the minus sign to indicate downward in our coordinate system. The mass of this object is 20 kilograms, and the acceleration has an amount 2.00 meters per second, but it's downward, so that's in the negative y direction. Very important to have that minus sign. So we can solve for F30 on 20. So we get that the magnitude of the force that the 30 kilogram block exerts on the 20 kilogram block is 156 newtons. If you ever get a minus sign for a magnitude, you know you've done something wrong, or else you're using notation where magnitudes and components end up having similar symbols, which is always dangerous. It can cause confusion. Okay, so now let's write this. But what about the direction? Well, the direction comes right off our picture here. We know that the 30 kilogram block is exerting a force upward on the 20 kilogram block. If it weren't, then the 20 kilogram block would be in free fall. There'd be nothing holding it up. So if we wanted, we could represent the full vector information. That is, the force vector that the 30 kilogram block exerts on the 20 kilogram block has a magnitude of 156 newtons and the direction upward. Now, here's where the power of Newton's third law comes in. If I know the force that the 30 kilogram block is exerting on the 20 kilogram block, by Newton's third law, I should also know the force that the 20 kilogram block exerts on the 30 kilogram block. Those forces have to be equal in magnitude and opposite in direction. So I can immediately write this. The force that the 20 kilogram block exerts on the 30 kilogram block must have the same magnitude, 156 newtons, but must be in the opposite direction, that is, downward. Now, let me reiterate the point I made about Newton's third law earlier. Both of the following statements are true. The first statement, which is Newton's third law, says that the force vectors that the two blocks exert on each other are equal in magnitude and opposite in direction. The second statement just is a relationship between the magnitudes, saying that those two forces have the same magnitude. This is contained in this. Watch how that comes into play when I draw a free body diagram of the 30 kilogram block in order to solve for more stuff in this problem. So this is representing the 30 kilogram block. I've labeled it with 30 kilograms, so I know what block I've drawn the free body diagram of. This 294 newtons is just 30 kilograms times 9.8 meters per second. That's the gravitational force acting on the 30 kilogram block. This force here is the force that the elevator floor is exerting upward on the 30 kilogram block. This here is the force that the 20 kilogram block is exerting downward on the 30 kilogram block. Now, we already know what the strength of that force is. We've already solved for that. That's 156 newtons. So when we write our free Newton's third law expression for this, we can plug 156 newtons directly in for this right away. Also, let me note I'm going to use the same coordinate system. I'm going to take upward as the positive y direction. I'm going to do that throughout the rest of this problem as well. Okay, so let's now write out our Newton's second law expression for this 30 kilogram block. The sum of the forces acting in the y direction on the 30 kilogram block must equal the mass times the y component of the acceleration of the 30 kilogram block. Alright, so this m will be 30 kilograms, this must be the acceleration of the 30 kilogram block, etc., and so forth. So let's plug everything in. So we have this, where we've replaced it with 156 newtons. We have a 30 kilogram mass, and the acceleration, it's 2 meters per second in the downward direction, which is negative in our coordinate system. Note, of course, all these things, elevator, the blocks, etc., they're all moving together. They must all be accelerating at the same rate. Okay, so now we can solve for this. So we can conclude that the magnitude of the force that the elevator floor exerts upward on the 30 kilogram block is 390 newtons. And of course we can write this information in vector form. The force vector exerted upward by the floor on the 30 kilogram block is 390 newtons upward, just as indicated in the diagram there. Now of course there's a Newton's third law pair to this, which we can write down immediately. By Newton's third law, the force that the 30 kilogram block exerts on the floor must be 30 newtons in magnitude and downward in direction. So here's a Newton's third law pair. So now we have all the contact forces. We got the force that the 30 kilogram block exerts on the 20 kilogram block, the force that the 20 kilogram block exerts on the 30 kilogram block. Those are a Newton's third law pair. We have the forces that the floor exerts on the 30 kilogram block and vice versa here. Those form another Newton's third law pair. So now technically we're done with the problem, but as a check I want to show another way you could get the force that the elevator floor exerts upward on the bottom of the 30 kilogram block. We could do that directly. We could consider this whole 50 kilograms worth of stuff as a single object. After all, any object is made of other objects, so we can actually pretend or imagine that all of this is a single object and draw a free body diagram of that single composite 50 kilogram object. When we draw that free body diagram, we won't include the forces that these blocks exert on each other. Those forces are internal to the system. For the same reason that in this free body diagram, I don't show the force that this molecule in the box exerts on this molecule on the box, etc. We're only showing external forces acting on the system. If I consider the 30 kilogram block and the 20 kilogram block as part of the same system, I will only include the external forces acting on that system in the free body diagram, because that's what will accelerate that system as a whole. So let's see how that all works out, and we'll make sure that we get this this same result. So here's a free body diagram of the 50 kilogram entity. So we've got 490 newtons of gravity acting downward. That's 50 kilograms for this whole entity times g. We've got the force that the elevator floor exerts upward on the bottom of this composite object, which I'm now labeling as the 50 kilogram composite object. And that's it. I don't include the forces that these two parts of that object exert on each other because those are internal to the system. They don't accelerate the system that we now are considering. Alright, so that's the free body diagram for this object. Let's apply Newton's second law and see what comes. The sum of the forces acting in the y direction on this 50 kilogram composite object is equal to the mass of that object times its acceleration in the y direction of that 50 kilogram composite object. Okay, so let's plug in. This force is here. This one is here, minus sign for our coordinate system. The whole thing is accelerating at 2 meters per second downward, which is negative in our coordinate system. And now we have a 50 kilogram entity that we're considering. Okay, so let's solve for the force that the floor exerts upward on this composite object. So we get that the magnitude of the force that the elevator floor exerts upward on the bottom of this 50 kilogram composite object is 390 newtons. That's just what we found for the force that the elevator floor exerted upward on the bottom of the 30 kilogram object. Now we had different labels, but the bottom of the 30 kilogram object is the bottom of the composite 50 kilogram object. So those forces are really referring to the same thing. They're just different labels because of the different ways we've considered our system, but our results are in agreement. So this is very good. It all checks out. All right, that's the end. Hopefully now you have a better understanding of how to apply Newton's second law and Newton's third law together to analyze a rather complex system.